Hello everyone. Welcome to this new lecture on multiple input and multiple output systems. So basically, multiple input, multiple output wireless communication systems employ multiple antennas at the transmitter and multiple antennas at the receiver. We'll look with the help of a diagram that how essentially multiple input, multiple output systems look like, and subsequently we'll also be discussing the very basic receiver for a MIMO system. So basically we have multiple input multiple output system. This is essentially our system is, and this is also known as MIMO system. Essentially what we were talking about was that it has multiple antennas at the transmitter side. So in a general communication system, we have a transmitter and we have a receiver. This is a very general communication system. We have a transmitter and we have a receiver. Now in MIMO systems, we have multiple antennas at the transmitter end. That means that the transmitter will be transmitting signals through multiple antennas, and at the same time the receiver will also be receiving the signals with the help of multiple antennas. And the links between these multiple transmit antennas and receive antennas will look like, we'll have basically a link between the antenna number 1 at the transmitter side, like this is the antenna number 1 at the transmitter side, this is the antenna number 1 at the receiver side, this is the antenna number 1 at the 2 at the transmitter side, antenna number 2 at the receiver side, and so on. This is the antenna number 3 at the transmitter side, we have antenna number 3 somewhere here, and then finally suppose we have the T transmit antennas that we are having here, and we have R receive antennas. So we have T transmit antennas and R receive antennas, and each of the signals that are transmitted from each of these antennas. So the signal transmitted from the first antenna will be received at the first antenna also. The signal transmitted from the first antenna will be received at the second antenna also. It will be received at the third antenna also, and so on. And finally, it will be received at the RF antenna also. Similarly, the signal transmitted from the second antenna will be received at the first antenna. It will be received at the second antenna, and so on. And finally, it will be received at the RF antenna. Similarly, from the third antenna also, the signal it transmits is received at the first antenna, it will be received at the second antenna, and finally it will be received at the RF antenna. And for the TF antenna also, the signals that it is transmitting will be received by all the R antennas at the receiver and that it will be receiving. So now we know that basically a multiple input, multiple output system has multiple antennas that can be employed to increase the reliability of the signal through diversity. Essentially, we can see that we are exploiting diversity here. So we are exploiting diversity here. We are essentially exploiting diversity here, and at the receiver end, at the receiver and the signals are combined through diversity techniques. Okay, so basically through diversity combining technique. Okay, so this is a particular multiple antenna, multiple input, multiple output system that we are discussing. Now, when this happens, that multiple transmit antennas transmit multiple receive antennas to us, so it leads to the diversity gain and the net decrease in the bit error rate of the wireless communication system. As a result of the exploiting the diversity, basically, we achieve diversity gain and a net drop in the bit error rate. So now we can see that essentially there are T antennas. So the first antenna this time will be transmitting the signal X1. The second antenna will be transmitting a signal, let's say X2. The third antenna will be transmitting a signal X3, and so on. And the Tth antenna will be transmitting a signal Xt. Okay. So the transmit signal we get is basically it is obtained in the vector form, and this vector will look like X1, X2, and so on, and we'll have Xt transpose. Let us say if the signal copies are real only, so we'll have the transpose of this. Similarly, at the receiver end, what we have our receive antennas, and at each receive antenna will be receiving some signal. So suppose Y1 is the signal received at the antenna 1, Y2 is the signal received at the antenna 2, Y3 is the signal received at the antenna 3, and finally YR is the signal that is received at the receive antenna 4, RF receive antenna. So the receive signal vector will be given by Y bar, and that will be given as Y1, Y2, and so on up to YR transpose. Okay. This is essentially our transmit and receive antenna. Transmit and receive signal. Now, what about the channel gain? So the channel gain a general channel gain factor will be formulated as Hij, where J basically indicates the transmit signal antenna, and I indicates the receive signal antenna. What is meant by this is, if I say, for example, that if I'm talking about H12, okay, if I'm talking about H12 basically, okay, so this means that the second transmit antenna transmitted the signal that was transmitted from the second antenna. Okay, we have all these antennas here. I'll draw a clear picture here. 1, 2, 3, and so on. These are the transmit antennas, and we have the receive antennas 1, 2, and 3, and so on. These are the receive antennas. So this is one, this is one, this is two, this is two, this is three, this is three, and this is P, this is R. Okay, so when I'm writing H12, that means that the signal, the link between this antenna, this one, and the first receive antenna. This is indicates the link between the second transmit antenna and the first receive antenna, which means that in this example, we are talking about this link. Okay, so essentially now what we get here is that we have our transmit signal vector x1, x2, x3, and so on up to xt. And this is transmitted to a MIMO channel. And we receive y1, y2 up to yr. Okay, this is what we are getting. Now we have various combinations. We have P here, P transmit antennas here, R receive antennas here. Okay, so if we talk about the channel coefficient H, so there will be H11, H12, and so on up to H1 P, then H21, H22 up to H2P, and then so on up to HR1, HR2, and so on up to HRT. These many channel coefficients will be having. Okay, these many channel coefficients will be having, and they will form a vector of all these channel coefficients that is essentially indicating the link between the first transmit antenna, first receive antenna. Okay, this is indicating the link between the second transmit antenna and the first receive antenna. Okay, and so on and so forth. And this one is indicating the pth transmit antenna and the first receive antenna, and so on. For all these coefficients, we have the convention that we are following. This one will indicate the rth receive antenna. Okay, and the first transmit antenna. This is basically the first transmit antenna. Similarly, this is the second transmit antenna and the rth receive antenna. And here this is we have pth transmit antenna and rth receive antenna. Okay, this is essentially our matrix of channel coefficients. So we are having, as we can see that here we have the transmit signal vector, and here we have this one is the receive signal vector. So now if I write it in terms of a typical wireless communication system, the MIMO system can be written as the receive signal vector y bar will be obtained as, we can see that this channel coefficient H, channel matrix H, that multiplied by the transmit signal X plus the noise vector N. Okay, because at each of these receive antennas will be having AWGN noise. Okay, so basically this, if I write it in terms of, if I open this expression, if I write it in terms of vector and matrix, so I will obtain here, you can see that this is a vector, the received signal vector, and this is our channel matrix that we have already written here. So I will write it as H. This is our channel matrix, and this is our signal x1, x2, and so on up to xt. Okay, and this will sum with our N1 and 2 noise at each of the receiving antennas. Okay, now you can see that this matrix is basically an R cross T matrix. So this is an R cross T matrix. This is a T cross 1 matrix. So we can see that the product of these two will combinedly become an R cross 1 vector. This will be an R cross 1 vector, and this is therefore an R cross 1 vector. So each of these, with this particular expression, we can see that each of these received signal values can be expressed in terms of the channel matrix that multiplied by the transmit signal vector, and that complete thing added with our noise vector. Okay, so now the important point that we have here is our MIMO receiver. So how do we design the receiver? So a very intuitive receiver that comes to our mind when we see this particular expression y bar is equal to hx bar plus n. As soon as we see this expression, now we have this y bar, this vector y, that is available at the receiver, and from the vector y we want to recover x. Okay, we have vector y available. We want to recover x from it. Okay, so a very general kind of mathematical strategy that comes to our mind is that what I do is that if I know the channel matrix H, I can multiply H inverse with y, with the vector y. So what I'll get here, x bar, that is the signal transmit signal vector, and that will be added with H inverse and noise vector. And since I'm knowing this channel coefficient matrix H, I can cancel out with the particular noise cancellation technique that I'm employing at my receiver. I can cancel out this part and I'll retrieve this signal. That was the transmit signal. However, the point that we have to note here that for this particular technique to be realized, we need to have H. Okay, the requirement is that H must be a square matrix. And for H to be a square matrix, we will need for H to be a square matrix. What we need is R equal to 2. However, this is a very specific case. In most of the cases, we don't have R equal to T. Okay, R equal to T means that the number of receive antennas should be equal to the number of transmit antennas, and that case is very difficult to be realized, as in most of the cases we have R is greater than or equal to T. So this particular technique is difficult to be implemented. However, now a general receiver technique that we want to employ, that is also called as a zero forcing receiver. And this zero forcing receiver is based on the essentially the basically the process, the least squares minimization technique. The least squares minimization technique. Least squares minimization technique says that the difference between our received vector y and the transmit signal x multiplied with the channel coefficient and the square of the second norm, if I have this particular factor, has to be minimized, and I have to choose the x that minimizes the square of the second norm between y bar and hx bar. So basically this is, we can say that this is a kind of error that we are receiving. The error that is existing here is expressed in the form that we have written here, basically. And this minimization of error is what we have to perform. And to perform, we have to essentially obtain the transmit signal vector x that minimizes the factor y bar minus hx bar. This is essentially square. This is essentially the concept of the zero forcing receiver. Okay. So we start with the zero forcing receiver, and you'll see that how we are essentially going to obtain the vector x that which minimizes the estimation error. Essentially, we can also call it as estimation error. Essentially, this is what this is basically the estimation error that we are going to have. Okay, so I have f of x bar that is given as y bar minus hx bar square. Now I want to perform the minimization. I want to do minimize this particular factor, and I have to search the x bar, the vector x for which this gets minimized. So whenever we have to search for a variable x that minimizes a particular expression, what we have to essentially do, we have to differentiate that particular expression with respect to the variable x, because since we are searching that optimal x only, and the differential of this function with respect to x has to be equated to 0. And after solving this, particular expression, the x which is obtained is the optimal x. Okay, so let's start with that. So our function fx can be written as, this particular square of the second norm can be written as, we know that y bar minus hx bar transpose multiplied by, we have complex variables here, but for our calculations as of now, we assume x, h, and y, such as a matrix only, to be real. Okay, so we have y bar minus hx bar. Now we have to use certain properties of the transpose. So what properties of transpose we are going to use, I'll write here. So if we have a plus minus b transpose, we have it as A transpose plus minus B transpose. Then the second property that we will be using is if we have AB transpose, so this is basically B transpose multiplied by A transpose. If we have ABC transpose, so that is basically C transpose B transpose multiplied by A transpose. Okay, and then suppose if we have another property that we'll be using is if we have the transpose of A transpose, so that is basically A only. Okay, so we start here. We can see here that this particular factor will be obtained as Y transpose minus HX transpose, and this multiplied by Y vector minus HX vector. Okay, so this will be obtained as Y transpose minus, we'll have here X transpose, H transpose, and Y bar minus HX bar. Okay, so I open the bracket, so I'll get here Y transpose multiplied by Y minus I get Y transpose multiplied by the channel matrix H multiplied by the vector X minus I get X transpose H transpose Y, and the last term that I'll get is X transpose H transpose HX. Okay, this is what we obtain here. Now we can see that if I look into, we have to basically do some mathematical manipulations here to simplify this expression. So we can see that if I say that in this expression, if I say in this particular expression, you can see that this Y transpose is what? This is basically 1 cross R. This H is basically what? This is R cross P. And this X is basically we have P cross 1. So when 1 cross R will be multiplied by R cross T, the resultant of this will be given as, will come out to be 1 cross T. And then when 1 cross T will be multiplied with P cross 1, the resultant of this completed thing will be a scalar. We will get a scalar value. So this means that our Y transpose HX is a scalar. Okay. So when we have this particular part as a scalar, I can write it as if Y transpose HX is a scalar. Okay. It means that the scalar, suppose I have a scalar A, for example, if I have a scalar A, so the A will be equal to A transpose if I have A is a scalar. So this will mean that the transpose of a scalar, the transpose of a scalar is the scalar itself. Okay, this is the concept we will be using. So we essentially have Y transpose HX. I write here the transpose of this will be equal to Y transpose HX. So I take this and I take this transpose inside and I use this particular identity. So I'll get here, what we get here is this comes out to be X transpose, S transpose, and Y. This becomes equal to this particular thing. So coming back to our error expression, that is f of x that we are having. I'm rewriting it here. Our f of x becomes equal to, we have here y transpose y minus, we have here, see, y transpose hx will be written as x transpose y, and this becomes minus x transpose y. This will be added with x transpose h and x. So this gives us what it will give us. It will give us y transpose y minus x transpose. These are the two factors. So we have 2 times x transpose h transpose y minus we have x transpose h transpose h and vector x. Okay. So this is our error function, that is f of x, and that is what we have to now minimize with respect to for finding out the optimal vector x. Okay, so let me rewrite it here. We have the minimizing function that we have obtained is y transpose y minus we have 2 times x transpose y and plus we have x transpose h transpose h and x. Okay. Now, as we discussed earlier, that if we want to minimize this f of x and to find out the optimal minimize f of x to obtain the optimal x. Okay, to do this, what we will do, we need to differentiate f of x bar with respect to x bar. Now, before we proceed here, we need to look into some things that are related to vector differentiation. So I will take a particular function. Let us say that if I have a particular function of a vector x, okay, we have a particular function of a vector x, and as we know that the vector x is nothing but we have x1, x2, and so on up to xt. This is our vector x. So now we have this in the form f of x, and I want to find out the differential of this vector, of this function of this vector x. So what that differential will be, this differential will be that we will be differentiating this particular function first with respect to the first value of x, then we will be differentiating this function with respect to the second value of the vector x, and so on, and finally we will be differentiating this function with respect to the ph value of x. Okay. Now let us say that, consider an example where we have the f of x as equal to some vector c transpose multiplied by the vector x. Okay, and c, this vector c is given as c1, c2. This is of the same length as that of x. Okay, this is basically our vector c. Okay, now this kind of function we are having. Now, if I start finding the differential of this function with respect to x, so what I will be having, I can see here that I will be having the differential of this function first with respect to x1. Okay, so what is essentially this c transpose into x? I can see here, we can see here, this is our C. The vector X is our X1, X2, and so on up to XT transpose. Essentially, that is what we are having. So if I try to find out this f of x, so we can see that C transpose, that means the C in the row form, C1 to CT, and this X transpose of this. So this in the column form. So we'll obtain it as C1 X1 plus C2 X2 plus C3 X3 plus and so on up to CPXT. Okay. Now I differentiate it with respect to XC. Okay. So the first factor that comes here is some factor will come here, all this factor and then this factor and then all these factors will come here. So the first factor, that is dfx by dx1, that will be dfx by dx1, that will be simply C1 from here. dfx by dx2, that will be simply C2. From here I'm doing this, finding only fx by dx1, dfx by dx2, and so on. I go on doing this, dfx by dxt, and so on. So when I do dfx by dx1, I'll get C1. When I do dfx by dx2, I'll get C2, and so on. And finally, I'll get here the value that is CT. So this comes out to be C. Okay. So which means that if I have a particular mathematical function that is C transpose X bar, the first thing is that it can be written as equal to X transpose vector C, that I leave up to you. You can calculate and see that both of them will be equal, and the differential of both of them with respect to X will be equal to C. Okay, this is what we are going to use now. So okay, so this thing we have now. Suppose we have to write write the function that we had already written here. So we have x f of x bar, and that will be equal to, we have y transpose y minus, we have 2x transpose h transpose y, and minus last term is we have x transpose h transpose h and x. And the concept we are going to use is that if we have a function f of x that is given as C transpose x, or that can be also written as x transpose C, so the differential of this function with respect to x, that becomes equal to C. This is what we are going to use. Okay, so now I differentiate dy dx of f of x. When I differentiate it, so the first thing here, I won't have any x, so this will be 0. The second term, in the second term, I can see that this is in the form xtc. We have it in the form xtc, so I'll separately consider this 2x transpose h transpose y. Okay, this is in the form xtc. So if I differentiate it, the differential of this will give C. So C here, then we have C is equal to 2 times S transpose Y. This is vector only. Even if I forget to write the bar here, this is always a vector. These are all vector. So the differential will be obtained as 2H transpose Y here. So here we get 2H transpose Y bar. And this term. So here we will need to apply the product rule. If we apply the product rule, the first thing we will see that this will be, I'll write down here, write it down, X transpose H transpose H and X. This is what we are having here. So now we basically want to differentiate it d by dx. So we'll get here the first time we have is the first term we'll have X transpose multiplied by C. So what will be remaining? The remaining term will be H transpose X bar. Okay, because we have X transpose into C. And then the second term we'll be having X bar. When we have X bar, we have C transpose X bar, so we get C. Okay, we have C transpose, and any vector can be written as suppose we have any vector A, so vector A can be written as the transpose of A. Transpose of the transpose of A is actually A. So this, apart from all these values, they are basically the transpose of transpose. Okay, so I'll get here X transpose H transpose H, the transpose of this entire thing. So when we finally get into the take this transpose inside, we'll get here as this thing as H transpose X H, and this will be H transpose H. Sorry, something. Sorry, this will be H transpose H X. Okay, earlier it will be H transpose H X, so that will be obtained as 2 times H transpose H X. Okay, so coming back to our differential term here, the differential df x bar dx, that will be obtained as minus 2 H transpose y bar. Here it is plus. Just checking the expression before. We have this is plus. Here it is plus. Okay, so here it is plus, and we get here the differential of this term is obtained as we have 2 times H transpose H and X, and this, for obtaining the optimal X bar, we have to equate it to 0. So when we equate it to 0, we get here 2 and 2 will automatically get cancelled. We have here H transpose y bar will be equal to H transpose H X bar. So if I try to write X bar will be equal to H transpose H, the inverse of this factor, and H transpose, and this multiplied by the vector y. This is essentially the X that will lead to the minimization of the least square estimate. So this X bar will lead to the minimization of the least square estimate. Okay, so that's all for today. We'll continue from here if a following lecture comes. Okay, I think this much must be quite clear. We have tried to deal it in the most simple manner as possible. So essentially we have We started with a particular MIMO system. We can see where T is the length of the transmit signal, as T is the number of transmit antennas, and R is the number of receive antennas. You can imagine it as like having a particular any transmitter, any base station or any transmitter that is having T number of transmit antennas, and the receiver, your mobile receiver or any other kind of wireless receiver, that is having R number of receiving antennas. So basically, when T number of transmit antennas are there, so X, the transmit signal vector will become like, there will be T number of transmit signal values, and those T number of transmit signal values will form a transmit signal vector. Similarly, when it will travel through the wireless environment, finally it will reach up to the receiver antennas, and suppose there are R number of receiver antennas, so R number of receiver antennas will be having R number of received signal values, Y1 to YR. So these R received signal values will form a received signal vector that has the components Y1, Y2 up to YR. And each of these transmit antennas are having a link with each of the receive antennas. So we will be having a channel gain matrix that will be containing all the coefficients between the first transmit antenna and first receive antenna, first transmit antenna and second receive antenna, first transmit antenna and third receive antenna, and so on. Second transmit antenna and first receive antenna, second transmit antenna, second receive antenna, second transmit antenna, third receive antenna, and so on. So such kind of channel matrix that is having all those coefficients that are signifying the channel gain between the first transmit antenna and first receive antenna, second transmit antenna, second receive antenna. All these coefficients that it is containing is our channel matrix, and we will be obtaining the our model, our received signal model will be modeled in this form, as we have already done. That is a received signal that will be equal to the transmit signal, which is multiplied with the channel matrix, and it will be added with the AWGN noise that is at each of the received antennas. And then essentially we'll be designing a MIMO receiver so that we are able to recover the signal X from the received signal Y, because whatever we have received at the receiver end, at the R receivers, is this Y vector only. From this Y vector, we have to recover X vector. So that is basically our goal. To achieve this goal, we will try to find out the transmit signal vector that minimizes the least squares error estimation of this particular system. The least squares error estimation is given by Y bar minus H multiplied by X bar. Okay. And finally, we will be performing these calculations to reach to the final solution that is given in the manner X bar, that comes out to be S transpose into H, the inverse of S transpose into H, that multiplies with S transpose, and this entire thing multiplied with the received signal Y bar. If we are choosing the transmit signal vector with this particular expression, this will minimize, this will lead to the minimization of the least squares estimate of the error. Okay, so we will continue with it in the next lecture. Thank you, everyone.